So we saw that u given by 1 over square root 4 pi dt times the exponential of minus x minus mu squared over 4 dt is a solution of the heat equation. So what initial condition does this correspond to? So in other words, what happens when we take the limit as t goes to 0 and look for ux comma 0? Well, it's a little strange because here's what's going on, right? This t in the denominator is going to make most values go down to 0, except if you're right close to mu, in which case this is going to blow up because of the t right here. So we have this increasing peak concentrated at mu, and for each one of these functions, as t gets smaller and smaller, the integral of this whole thing should equal 1. So let's take a closer look. So recall that the probability of finding x at time t between a and b is given by the integral from a to b of this solution that we found before, right? So that's the probability of finding x in the interval. So this is, maybe I'll just write that. The probability x is in the interval from a to b at time t. Okay. So let's see. So if we choose an interval so that the mean mu is not an element of that interval, so if b is less than mu or if a is greater than mu, then what happens is the limit as t goes to 0 of this probability is going to be 0. And so you can see this because if we've got, and so here I'll do some terrible doodle of what's going on. So suppose I take my interval from a to b to be out here, so b is much less than mu, then what happens is the curve is going to be, something like that for t very small. Now it is actually positive everywhere, but it's so close to 0 that the area under the curve in the interval from a to b is very close to 0. And as t gets smaller, then that actually does go to 0 in the limit. So that's what's happening. So conclusion, the probability of our random particle becomes concentrated at the mean. And in the limit, the entire probability measure is going to be right at mu. And so what we call this a point mass at mu. And so examples of this kind of distribution. So this is an example of here. So this probability distribution is not given by a continuous function. Not given by a continuous function. It's what we call a discrete distribution. So examples of discrete distributions are actually familiar. If you think about it, in fact, they're probably more familiar than anything else. So, for example, suppose we let the random variable y be the outcome of a fair roll of a usual six-sided dice. Right, so we roll the die, and what happens? Well, then the distribution of y looks like like if you were going to try and graph it, well, it's not a continuous function per se. It's going to be something like this. So let's see. So here's 1, 2, 3, 4, 5, 6, and those are the only things that can happen. So this can happen, this can happen, this can happen, and there's little point masses at each of these possible outcomes. There's no point mass, say, at 3/2 because that's not a feasible outcome. And each one of these comes with weight 1/6. So these are supposed to be so that's because there's only certain outcomes that can happen. It's the random event is not continuously distributed. So in this case, the probability that y takes a value between a and b, it's not going to be represented as an integral. It's actually going to be represented as a sum. And just for shorthand, I'll say it's going to be the number of points in the intersection between this set here, 1, 2, 3, 4, 5, 6, and the interval a and b. So the number of integers which are in that set, well, in both of those sets, and then divided by 6, because that's the total number of possibilities. Okay. So this solution that we found, given by the normal distribution, is the solution corresponding to a point source. So, in other words, U solves the equation ut equals d u xx with u of x0, the initial condition being delta mu, where delta mu is the Dirac delta located at mu. So the Dirac delta is not actually a function, it's a measure or a distribution, if you prefer to call it that, and it corresponds to a point mass. So all the weight, all the probability weight is located at a single point. And so this u that we found that's given by the normal distribution is what's called the fundamental solution. Of the heat equation. More on that in the next video.